lecture will also be in two parts, as I also just reiterated. It will be one and a half hour each, with a small 15-minute break in the meantime. After the break, we will be staying in the same Zoom webinar session. Also, the YouTube live stream will go on, which will start in a few minutes, I think. Oh, we are live there.
Yes, we are live. Yes, I did it.
This is the lecture titled Deep Feature Extraction and Classification for Hyperspectral Imagery. The lecture will be given by Behnood Rasti from the Machine Learning Group of Helmholtz-Zentrum Dresden-Rossendorf in Germany. And I will now give the stage to Behnood. Thank you once again for being our invited lecturer. And you should be able to share your slides now.
Okay. So I guess you can see my slides now.
Yes.
Okay.
See the first page.
Yeah, great. So thanks, Alp, for the introduction. So my name is Behnood Rasti, and I'm with the Machine Learning Group at Helmholtz Institute for Freiberg. And this talk is about deep feature extraction and classification for hyperspectral imagery. So these are the objectives of this talk. I kind of arranged all the slides and the topics in a way that everyone with any kind of background can follow the lecture. So we go from some basics and materials into some advanced. So we start with the concept of feature extraction, and we briefly go through some shallow feature extraction techniques, and then we discuss deep feature extraction, and we study basic deep learning architectures, and then in the end we compare shallow feature extraction versus to deep feature extractions and I show some results. And finally, I introduce a toolbox, HyperTech. It's called HyperTech, Hyperspectral Deep and Shallow Feature Extraction Toolbox. And hopefully, if I get any time, I can I can kind of help the audience to work with these toolbox. We start with hyperspectral images. Hyperspectral cameras provide continuous electromagnetic spectrum. Therefore, instead of having a few bands, you have hundreds. You might have hundreds of bands located at different wavelengths. And this spectral signature is very valuable because it allows to distinguish between different materials. So that's basically the difference between hyperspectral images with multispectral and RGB images. But then we have kind of different type of challenges with hyperspectral, particularly when it comes to deep learning. Hyperspectral sensors have different spatial resolution, spectral resolution, and spectral ranging. And for deep learning, hyperparameter tuning and architecture design is very challenging in such these kind of cases. And we always, particularly for remote sensing application, we often have very limited training samples, which is also challenging in the case of deep learning, using deep learning techniques. So what is feature extraction and why do we use feature extraction? In feature extraction, basically, we are searching for a few informative features which can represent our data and help us to classify our data. At least there are three main advantages using feature extraction. It's saving storage space or faster transmission, and it helps to improve the classification considerably, and it also saves time. So with hyperspectral images, we get more information, but then also the higher dimension that other type of images. This higher dimension provides much more or need much more statistical parameters to select, and then therefore it often decreases the performance of conventional technique. And this is called curse of dimensionality, and it was the case for conventional techniques, and feature extraction could considerably help to kind of cope with this problem. So why we don't use spectral features? So as we said, high dimensionality or curse of the dimensionality, redundancy, saving storage and computations. And another important thing is that hyperspectral images have low spatial dependency or resolution. And so it turns out that if you can extract this spatial dependency with some techniques, you can considerably improve the classification accuracy. So conventional machine learning techniques for classification of hyperspectral images had two steps. First, applying a feature extraction or reduction technique, and then applying supervised classification such as random forest and SVM. And then basically getting our final classification map. And shallow feature extraction techniques can be divided in two categories: unsupervised and supervised. And unsupervised techniques do not incorporate label samples or ground references. Instead, they capture the intrinsic characteristic of the hyperspectral data, such as geometric, spatial, or spectral information. And on the other hand, supervised feature extraction techniques rely on the label samples, and they extract class separable features. Just briefly reminding everyone about the definition of norm before moving forward. As a function which maps a vector space to the non-negative real numbers, and it's a definition of P norm, and L1 and L2 is the most common one that we usually use a lot. And L1 is basically the summation of absolute values, and L2 norm is the basically square root of the summation of the squared values of your vector. So in unsupervised feature extraction technique, you're searching for projection matrix or subspace bases sometimes they are called, while capturing the unrestricted characteristic of the data. So, for instance, we're in PCA, we're searching for subspace which maximizes the variance. C is here the covariance matrix, and for NMF6, a projection to maximize the signal-to-noise ratio, and CN is the noise covariance matrix. And when you have your basically subspace basis, then you can project your data into the subspace. A little bit more advanced techniques, we model our data a little bit differently. So the input data is multiplication of few representative features times with subspace basis plus noise. And for instance, this technique, which is called orthogonal total variation component analysis, uses this model, or in short, OTVCA, and suggests to solve this minimization problem, which is the combination of a fidelity term on the left and then a total variation penalty subjected to orthogonality constraint. So total variation penalty basically promotes piecewise smoothness on your features, especially, and considerably helps to improve the classification accuracy. So basically, in supervised feature extraction technique, we have a set of samples with the corresponding class labels, and we want to find a transformation matrix P, which optimizes certain class relevant separation criteria. And then when you estimate your transformation matrix, then you can project your data to the subspace. So linear discriminant analysis is one of the basic supervised technique. Estimates the linear projection matrix P that maximizes this ratio. SP is the between class covariance matrix, and W is within class covariance matrix. Indeed, we are searching for P, which projects the samples of different classes as separable as possible, while decreasing the variation of the samples within each class. And joint learning is one of the advanced supervised feature extraction techniques. It simultaneously learns the subspace basis theta and the regression matrix P that applies on the samples. And basically, there's a fidelity term. YL is the label matrix, and then we hold the orthogonality constraint and the subspace basis, and also use a penalty term, previous norm penalty term on regression and the regression matrix. So that was a very brief review of shallow feature extraction, and now we move to deep feature extraction. So as we said already, in conventional machine learning techniques, we apply first feature extraction, and then or feature reduction, and then supervised classifier for the classification task. And so basically, deep learning techniques automates this process. So to just give kind of intuition how shallow feature extraction techniques are compared with deep networks, we can say that shallow feature extraction techniques often require careful engineering and domain knowledge of expert, but deep networks can automatically learn high-level features from raw data in a hierarchical fashion. Deep features are more discriminative, abstract, and robust than shallow ones. And in this tutorial, we study 5 basic networks: autoencoders, convolutional autoencoders, convolutional neural networks, recurrent neural networks, and convolutional recurrent. So before starting to explain those networks, I want to remind you about the challenges of deep feature extraction techniques. We have limited number of training samples. Often selection of the architecture is always difficult and might vary with respect to the data set and the sensor. Hyperparameter tuning is a big challenge, and in this tutorial we will answer this question, that if these basic networks can outperform the shallow ones in terms of classification accuracy. And by the way, if you have any question, if somebody, because I'm not following the chat, if somebody let me know, then I can answer immediately. You don't have to wait until the end of the lecture. So we start with CNN and explain convolution. Convolution, basically you have a filter. In this case, it's edge detection, and you convolve it with your image, and you basically slide the filter to your image, and you calculate the values, and then basically in this way you're extracting some features. But why do we need convolution is the main question here, and I would like to know if somebody can answer these in chat, or I wait for a couple of seconds to see if I get any answer. So what's the main point of applying this convolution, and why CNN is one of the most effective network out there in different machine learning area or applications? Yeah, to generate more relevant features. Yeah, basically one of the reasons is to extract the spatial information, and that's the main power that comes from this convolution. And also you get less parameter compared to fully connected neural network. And also convolution is transition invariant, which is very important in some application like object detection, for instance. So convolution with padding, and So yeah, we often apply padding for a different reason. And actually, we have a different type of padding. What you're seeing here is zero padding, and you can also have kind of mirror padding, which the values are mirrored basically, or different type of padding. And yeah, the main reason, I can say at least two main reasons for using this type of convolution with padding is that sometimes in some application you don't want to you want to avoid shrinking the spatial size of your data, and you want to also you want to extract information in the border. So with padding you can basically solve these problems. Then we have a striated convolution. So as you see, instead of moving one value in this case, which is striated, is 2, you move your filter every other row and every other column. So, and that's what's called striated convolution. And in this case, the horizontal and vertical stride is 2. And basically, in this way, you can decrease the parameter of your network. And then we have convolution over bands, and this is when you have not just a grayscale image, but more bands, such as hyperspectral images, and then basically use different or filters, multi-channel filters. And as you see, when you apply your filter in this image with when you apply your filter with your image, then you get one output, or when you convolve it, you get one output. And in this case, we use 2 filters, and then basically you concatenate the outputs of the filters. So basically, the number of bands of your output is the number of filters that you select. So this is called convolution over bands, or convolution volume. Another component in CNN is pooling. In this case, you're seeing max pooling. We also have average pooling or other types of pooling. These are 2 main types of pooling. So in this case, the filter size is 2, and stride is also 2. And inside your filter, you basically select the maximum value. And in the case of average pooling, basically you take the average value. In some cases, you can extract better features, and also using pooling, and also it decreases the parameters of your network. You're kind of downsampling the spatial sense. And finally, we have activation function. There are different types of activation function, and they all try to apply nonlinearity to the learning process of your network. And for instance, sigma is between 0 and 1, and tanh is between -1 and 1. ReLU just keeps the positive value and neglects the negative value. And you have the leaky ReLU and ELU, which slightly work different when for the negative value compared to ReLU. And I would say ReLU and leaky ReLU are the most common one to use in deep networks. So this is simple CNN, and we have two filters, and then after the convolution, we concatenate the outputs, and we add the bias to it, and we apply the activation functions, and you get the output. And this is just a convolutional layer. Obviously, in a deep network, you have several of these sequentially, basically one after the other. So the main question here is how to estimate the values. By the way, the values of the filters are called W, often the weights. And the reason that it's empty here, because we need to estimate them. And also we need to estimate the bias. These two are the parameters of your network, and anything else, such as the size of the filter, and number of strides, and anything else consider as hyperparameter of your network. So the main question is how to estimate these parameters, W and B. And yeah, there's no answer. So you need to use kind of algorithm to estimate these weights and biases. And in terms of gradient descent is one of the most effective one for this. And so I assume that we have a cost function with respect to W and B, and it's called J. And we can, and then gradient descent is given by these two updating equations or formula that to which estimates the value, the parameters W and B. And to explain a little bit more, we can see this figure, which is in this case, which is to simplify, we only use JW and we ignore B. So first we initialize the weight, and then we calculate the gradient of the cost function at this point. And in case of minimizing, we multiply it with a small parameter alpha or value alpha, and then decrease it in the case of minimizing. And we slowly move down the graph. And after updating the value W, again, we do continue the same procedure until we slowly converge to the minimum. So that's basically how gradient descent works. So you can see in this figure or animation better how slowly gradient descent converges to the minimum. So we need to initialize the parameters, select alpha, and calculate the derivative of the const function with respect to the parameter, update the variable or the parameter, and then repeat 2 and 3. But the main question is, well, in this case, it's easy to calculate the derivative for this correlative function. But how we can calculate the derivative or the gradient in a deep network? So that's the question that I would like to see if anybody has Any idea? I will wait a couple of seconds. Well, yeah, the question is written here. How can we calculate the gradient in a deep network? Somebody is asking to repeat the question. Okay. By using a loss function. Well, we have this loss function, or actually it is the cost function that we have. And but we need to calculate the gradient of the cost function with respect to the parameters that we have. How can we do that? It's, yeah, exactly. Finally, someone answered. So in a simple function, it's very easy to take the derivative. But in a deep network, it turns out the best solution is the back propagation or backward propagation through the network. And that's how basically, yeah. And when you want to use the derivative, to calculate the derivative, then you can use the chain rule as one of the audience wrote. So, yeah, backpropagation this is exactly where backpropagation comes to play. So forward propagation for one layer is given by these two simple equations, convolving your parameters, W, the input of the layer, and then plus biases, and then applying G, which is the your activation function. And then you get the output AL, and you need to actually cache ZL and AL -1 because you're going to need it in the back propagation. When you're back propagating through the network and calculating the gradient, this value, you don't want to calculate again this value, so you cache these values. So here is a kind of block diagram of forward and backward propagation and how generally a deep network works. And so let's assume that this can be any type of network, but now we're talking about the CNN. So you have your sample X, you give it to the network, you calculate. So first of all, before anything, you need to initialize W and P. Obviously, you need to initialize your parameters, and then basically you have your sample X, you give it through the network, you do all the multiplication, convolution, and calculations, and then you get an estimation by hand. And then through Y hat and the label that you have, you calculate the loss function, and then you calculate the cost function. And then you need to use this cost function and take the derivative of this cost function with respect to all the parameters or variables inside your network and backpropagate through the network step by step. So here actually DA, DB, and DW, they're a simplified version of DJ over DA, DJ over DB, and DJ over DW, and J is a cost function. And I don't go through the details of this, how is the formula for these variables and how to calculate it. But if you know the chain rule, as one of the audience said, it's very easy to derive these formulas. And then basically step by step, you back propagate, you have your formula when you derive it, and you back propagate through the network. And then you need to update when you get your new variable. Basically, when you calculate the derivative, you multiply it with alpha, and then you update your parameters. And that's how basically network works. And this is actually basically called training in your network. When you use training, it means using this process. Another important concept is mini batch gradients. So it turns out that, so basically you have a loss function, and then you have a number of samples as the m sample, and your cost function is the average over all the losses of the all the samples that you have. And it turns out that instead of using all the samples to calculate the gradient at once, it's better to split them into, let's say, in 2 mini batches, and try to basically update and or calculate your parameters for each mini batch. So as you see here, for instance, this is kind of pseudocode. So you have n2 mini batches in this case. You apply forward propagation on, let's say, n1 samples, and then calculate the cost function, and then backward on n1 samples, and then update the value. And then you would like to repeat these several times until you get the convergence, and that's what is called the number of epoch. So now that we have a kind of a good idea about the main components of CNN and maybe some other networks as well, to be able to convolutional neural networks and the architecture that we used. So basically the main blocks is convolutional layer, batch normalization, activation function, pooling layer, and fully connected. And batch normalization, it's basically normalizing the values at each layer, and that speeds up the learning process and provides more robustness in terms of hyperparameter tuning. So this is the architecture that we used, and yeah, somebody is asking a question about if there is more than one minimum, and how do we ensure we descend into the right one. Well, actually, there might be more than one minimum, but it turns out that in high dimensional data, this is not a problematic, and there and often you kind of look for a settle point, and you get to a settle point rather than the like global minimum. And that's why actually all these deep learning techniques are successful. Okay, move on with our convolutional neural network that we used, and this is the architecture that we used. And 3 levels of convolutions, and then we use batch norm, ReLU, activation function, max pooling, and then again another layer, and finally another layer, and then finally fully connected layer. Number of filters that we use, 32, 64, and 128 for count 1, count 2, and count 3. And filter size is 3 by 3. It's very common that we use. Everybody uses this. And it's very effective. And then trace entropy is the last function. And also we apply PCA prior to CNN in the result that in the next slide I will show you. And we call it PCNN, and simply we apply PCA to reduce the dimension, and then use few first principle components to fit to our convolutional neural network. Okay. If you have no question, I will move to results.
There is one question on YouTube.
Okay.
The question is, I would like to know what is the best way from satellite image using feature extraction. And this question is followed by another question, which software do you use, Torch, Colab, or others?
We use for this, all these deep learning techniques, we use the PyTorch. What was the first question? A PyTorch platform, basically.
Yeah, let me repeat. I would like to know what is the best way from satellite image.
What is the best what?
That's what is the best way from satellite image using feature extraction. I think, you know.
Well, I think you should just wait.
Feature extraction from satellite images.
Yeah, basically it depends on your application. This question is very general. What we are working here, it's just feature extraction for classification. And if you wait, you can compare the results of. We can see the comparison of the results of shallow feature extraction versus deep feature extraction, at least for basic networks. And for other application might be different, and definitely for advanced deep learning techniques might be different. I hope I answered your question. Yeah, another question is how much training samples or how many training samples are required in deep learning to classify data? Is there any rule method to select training samples in deep learning? Well, no, actually there is not, and it depends on your network and also your architecture and also your application. And sometimes you will be surprised that you get good results with few number of samples for training, and sometimes you cannot get good results with even so many samples. So there is no concrete answer to this question, unfortunately. Yeah, if did I answer? I think I answered. Why do you use PCA? I think I missed this question. Why do you use PCA? Doesn't CNN handle feature extraction by itself? So that's exactly what we're trying to see in the next slide and compare the results. So that's one of the That's basically one of the outcome of this study, that if you apply PCA, CNN works better, and it's unless you have to kind of manipulate your architecture based on the different data sets. So if you just apply CNN, it might work on one data set but not the other data set. And or you need to basically provide a much more advanced CNN. But this simple CNN, unfortunately, doesn't handle feature extraction by itself, as you see in the next slide and based on the results that we have. So I think we have more questions, but because of this question, I move to forward, but I promise you I will answer all your questions later on. And this is basically the answer to who was it? Hania's question. So let me finish this slide, and then I'll go again through all your questions. So this is the experimental results for different type feature extraction technique, and the comparison is in terms of overall accuracy with respect to the number of training samples. So basically we're using here 10, and then 25, and then 50 in 100 number of training samples. And the results are based on the Houston data set. So OTBCA, as we already said, is an unsupervised technique, and then you need to apply a supervised classifier for the classification purpose, and we use random forest. JPL is also is a supervised technique, and again it's a kind of advanced technique of joint learning technique. And then again, we apply random forest for the classification purposes. And then we compare the result with CNN and PCNN, which is applying PCA prior to CNN. And the blue line basically is only applying the random forest on the spectral bands. So as you see, applying random forest on the spectral bands provides very poor results. And then comparing OTBCA, which is an unsupervised technique, with the supervised technique JPLay, we get considerable improvements. And so CNN slightly outperforms OTBCA plus random forest in this case, we can say. But when we apply PCA prior, then we get considerable improvement compared to all the other techniques, supervised and unsupervised techniques. So that's one of the outcomes that we got from this study. But then again, as you saw the network, the CNN network, it was 3-layer, very simple network, and you might do kind of design a more complicated CNN and get much better results, or even you might tune your hyperparameter better to get better results. But then again, there's no guarantee that your network is not biased to one data, your data that you're working on. When you move it from one hyperspectral data to another one, the same network might not work properly. And that's basically what we're trying to say about the challenges of hyperspectral image classification using deep learning techniques. So let me read again before moving forward, because CNN is finished here, to see if there is any question that I didn't answer. Anonymous attendee, can we use CNN to find N members and abundance matrix? Actually, we can, but it's out of the scope of this lecture or tutorial. We recently developed a kind of sparse mixing techniques using CNNs. If you're interested, you can also find the code online. But yeah, there are often for estimating N members and abundances, you need to use kind of encoder-decoder architectures. And then basically the decoder part is the weights of the decoder part is basically your N members, and the final layer of encoder basically is your abundances. And most of the cases you apply softmax on your final layer to enforce the non-negativity constraint and one-to-one constraint. So yeah, that was the answer. Hope you got the answer, got your answer. No, basically, okay, another question is here. Did you design a new CNN or a pre-trained architecture like DenseNet or ResNet we used? No, basically, this is the exact architecture that I was talking about that we used, and there's no pre-train or nothing. And we train based on the samples that we have. Another question is, do you
We also have question and answer sessions at the end of the lecture, so if you want, you can leave the questions there also, as you wish.
Yeah, so yeah, I can take care of these questions, and we can move on to the next part after I finish these questions. There's only a few questions left. Do you have proved it for some complex networks too? I'm not sure by it what it refers to. So I'm not sure how. I don't know. It's I think it's Honey. That maybe you can rewrite your question in the end of the session better. And we have two more questions. That okay, maybe we can leave this to the Q&A session, because I can see that the number of questions is increasing. Let's also talk about autoencoder before moving to the Q&A session. Okay. So yeah, another architecture. So we talked about CNN so far, and now we want to talk about autoencoders. And in autoencoders, we have an encoder part and then a decoder part. So the encoder basically represent the data in a feature space, and then the decoded part basically tries to reconstruct the data using those representative features. Therefore, the loss function is also always based on a reconstruction error. So the error to basically we want to minimize the error between the reconstructed image and the input image. And yeah, the most important thing about autoencoder is that when you want to when the network the learning or the training process is finished, then you remove the decoder part and you use the encoder part as the classifier. And that's basically how the autoencoder works. So I think I will stop here before moving to recurrent neural network and answer your questions and leave the recurrent neural network for the next session. So get back to your questions. How do we know that the training examples we have are enough for deep learning? My thesis is crop mapping. Yeah, as I think I already answered this question. Basically, you need to see if you need to use your training samples and to train your network, and then see if basically you get good classification accuracy. And that's one way, by trial and error, that you can see if the network works. And another way is to and a practical way is to use or try to use different number of training samples. Let's say you have 100 training samples. You can start by using 10, 20, 50 and increase it, and to see if after one level if you get any improvement or not. And that's another way to kind of find out about the number of tiny samples that you need. Okay.
Behnood, if you want, I can also relay the questions from YouTube to you.
Yeah, sure.
We have a question by Samat Ismail. Can you replace the last fully convolutional layers of CNN architecture with shallow classifiers like SVM or random forest? And if yes, what is the limitation of this combination?
I don't think it's a good idea to if I understood correctly, you want to remove the final convolutional layer and then substitute with SVM, and I don't know how that works, because then after that you have a fully connected layer, and basically you are generating the labels. And instead, what you can do if you want to use SVM, you can use the features that you are extracting and feed it to SVM. That's one way to do it. But again, I don't think it's an effective method to. I'm not sure if it's gonna work out. Basically, the main point or main advantage of deep learning techniques is the end-to-end process that they have. And through some kind of learning these features, they generate the labels for you. But what you want to do, you want to substitute the final layer, which is the final layer, which basically it helps to train the network better with other classifier like SVM or other things. So in my opinion, that won't be effective. I think there was another question, Alp.
There are more questions from YouTube if you want.
Okay, sure. Yeah, sure, but I think there was also one question from...
In the Q&A, I think we answered those.
Okay, okay, good.
On YouTube, there's a question asked by Burak. The question is, I was wondering about the use of pre-trained weights. Is it convenient to use ImageNet weights for hyperspectral image processing?
Yeah, you can always use pre-train. For instance, in this autoencoder, we basically using pre-train. So we train the network and then use an encoder as the classifier. So yeah, but I never used it.
Another question is by Aninda Goswami. The question is the final layer doing a per pixel classification?
Could you repeat it, please?
Yeah, the question is the final layer, I guess in a CNN, doing a per pixel classification?
Yes, yes, exactly. So basically, you get the probability in the final layer for each pixel. Yeah.
Okay, that's it for the YouTube questions.
Okay. So, Yeah, what I want to do now, I would like you to, for some of you that have Python installed, you can go in, let me see. So during the break, for those who are interested in doing kind of hands-on in this tutorial, I would suggest you to go on this GitHub page, and all the materials that you need are there, and also you can find it in this feature extraction for hyperspectral imagery. It's a review paper on this topic. You can download the HiveTech or use HiveTech, and I can maybe in the next session or at the end of the next session, I can help you to work with this toolbox if you need. The deep learning part is based on PyTorch, and I think you need GPU. I don't think we provided CPU option for it. And so unfortunately, if you don't have GPU, you might not be able to run the deep feature extraction techniques. But then the shallow ones are based on the MATLAB, and you need to have MATLAB, and you also need to download the Houston dataset. I think we already provided the labels, like the training samples and the test samples on the website, on the page, as far as I remember. And yeah, I would like to ask you to go and download it, and to see if you can work with it and duplicate the results in this paper. So this is basically a collaboration with my colleagues, Dampen Hong, Relan Heng, Pedram Yamisi, Shudan Kong, Jocelyn Chanosud, and Yonati Benedictson. And yeah, I will be happy to help you to work with this. If you have any question regarding the toolbox, basically you can ask either now or later on, yeah, after the session.
Yeah, we have some time in this part of the lecture. If you want, we can go over either the paper or the toolbox, as you wish.
Yeah, sure. I can see one question here. Let me answer this. Pixel-based classification. Okay, pixel-based classification or object-level classification. Which one is more appropriate with CNN? Well, this is it's a hard question to answer. I would say it depends what type of CNN you're using, but for object level classification, there are other types of CNN that is more appropriate rather than simple CNN that we showed here. So actually the CNN that we showed here, it's basically for pixel-wise classification, and this classification often in computer vision, it's called segmentation, and then basically they use different terminology basically for this. And what we then there are other, in computer vision, there are other types of like mass Gaussian and Gaussian or faster mass Gaussian, which is a little bit more suitable for object detection problems. So I would refer to computer vision literature to basically better to find out your answer better regarding the object level classification. Okay. I don't think there's any answer here. Is there any answer on YouTube?
No, no questions at the moment.
Okay.
Which we can give the break early and then.
Yeah, we can give the break early, and then I will start with recurrent neural network.
Any other questions from the audience? I guess not. Okay. This Zoom webinar session will continue. We'll just be giving a around 15-minute break. The YouTube live stream will also go on, and after the short break, we'll be back. Thank you for your interest. Welcome back, everyone, to the second part of the lecture given by Behnood Rasti from Helmholtz-Zentrum Dresden-Rossendorf. The lecture title is Deep Feature Extraction and Classification for Hyperspectral Imagery. Behnood, are you ready to continue?
Yeah, sure.
Thank you.
So we can see my...
I think your mic is closed.
Sorry?
There's an issue.
Can you hear me?
Yes, now we can.
Okay. Can you see my screen now?
Yes, yes, we can.
Okay. So we already talked about CNN and autoencoders. The next architecture is recurrent neural networks, RNNs. And before that, I would like to know that if anybody downloaded the code and could run the codes, particularly for the deep learning ones. And maybe I should send the link to the dataset as well. But yeah, maybe Alp, you can do that if you can send the link for Houston 2013. So the audience can download the dataset. And
where is the link exactly? Do you have it?
I don't think I have it, but I guess I can, or maybe, hold on.
I don't also have it.
Hold on, maybe I have it here. Okay. Yeah, I guess you can download the Houston 2013 here, and then simply use the code, and I'll talk about it later, but most probably you can also work with it yourself. I'll go back to the lecture. So yeah, we already talked about CNN and autoencoders, and now we move on to RNNs, recurrent neural networks. So RNNs are suitable for sequential data, and you have your data at time, different time, x1, x2, x3, and x at time x. And then you have your output at time 1, time 2, and so on. And these are basically the weights and the parameters that govern this type of RNN networks. You have WAX, which is the parameter between the input and the hidden layer, and WAA, which is the parameter for the horizontal connections, and WYA, which is the parameter between the hidden layer and the output. And yeah, sometimes these RNN networks are shown with this loop, which represents the recurrent connection. But there's one problem with this type of network, and I would like to ask the audience, see what's the problem with unidirectional RNNs. If anyone knows the answer, just a few seconds. Somebody wants to type. What's the problem with this type of architecture, this type of sequential architecture? That's a question. I'm not sure what you mean by no feedback. Okay, we're getting there. Exploding gradients. Well, that's one of the problem with RNNs in general. Yes, unable to. Yeah. Okay. There are some good answers, which is all they're correct. But for this unidirectional RNNs, basically the network is from left to right. And for instance, in this case, Y3, output at time 3 depends on X1, X2, and X3. And there's no dependency on other times rather than these 3 times. And so how to solve this problem? How to solve what if our sequential data also depends on the values on the right side? Does anybody know? Make some connections. Oh yeah, okay, what type of connections? So somebody, I think Hani suggested make some connections. So what type of connections do we need? Okay, LSTM is another network, but how can we solve this network itself? So basically, I think there's no answer. So basically, one solution to this problem is using bidirectional RNN. And that's out of the scope of this talk. But as Hani suggested, you can also make connections from the right to left to solve this problem. And that's called bidirectional RNN. Not just only from left to right, but also from right to left. So this is equation for forward propagation. So WAA times A times minus, so it's at time t. WAA times A times minus 1 plus WAX times the input at time E plus the bias, and then you apply an activation function, which is G here. You get parameter E, and then parameter parameter A, sorry, and then if you multiply parameter A with WYA plus the bias, so weights in the bias between the hidden layers in the output, and then applying an activation function, you get the output. So this is a forward propagation for RNN. So these equations basically govern the architecture that I earlier showed. And we can further simplify this equation in using matrix form and only use one variable for the weights. And if you represent these two terms in a matrix form, then you can call WAA and WAX with WA, and then your equations will be a little bit more simplified, and this will be the basically the equations that you need for forward propagation. There's a question: is bidirectional RNN considered as back propagation? No, this is not considered as back propagation. It's just different concepts. Okay, so we can represent this RNN unit with a black diagram, and we have AT minus 1 and HT, and then we have our weights here and biases, and then the activation function basically here is tanh in this example, which produces AT. And then for output, again, you have your weights and biases applied on AT, and the activation function is softmax in this case. So sometimes people use these units with this kind of black diagram, and it might be a little bit simpler to understand the concept using these black diagrams. So, yeah, as we already discussed before, there's one problem with this, another problem with RNN, it cannot memorize long dependency. And as some of the audience suggested, it's because of vanishing or exploding gradients. So when you're backpropagating to your network, when the sequence is long, then basically you might often face this problem. And exploding gradient is easier to solve, but vanishing gradient is really hard to tackle. Usually exploding gradient can be simply fixed by using kind of clamping function. So instead, we can use gate and recurrent unit, GRU, to solve this problem. And as the audience suggested, GRU and LSTM, they basically don't have these problems. And so for GRU, we have a new variable called CT, which stands for the memory cell. So basically, we have a candidate called C tilde, a T, to replace CT. And then we have an update gate, lambda u, and based on the value of lambda u, we decide if basically CT should be updated with new variable or keep the previous value. So you can actually, to simplify this concept, maybe you can assume the updated gate value either 0 or 1, and then so if it's 1, then it's this term is 0, and then you get new candidate, and then if it's 0, basically you keep the value as it is and you don't update this variable. So you can also show these equations with this black diagram that it's very similar to the RNN with this extra CT, and in this case CT is equal to 80 and CT minus 1 is equal to 80 minus 1. So this is a kind of very simplified version of GRU, and again we are using tanh as a function, tanh for the CT and the good function for the updating the update gate basically. Then we have full GRU, and so the main difference between full GRU and the simplified version is that it has another gate called the relevance gate, and this gamma R basically is a relevance gate and decides how relevance is the previous value to compute the new candidate, which is C tilde. So you can assume it as this way. So this is basically the main difference and between full GRU and simplified GRU. And obviously this relevant gate has its own weights and bias, and similarly similar to update gate. So this is this is how GRU work, and it might be a little bit more complicated as RNN, but it works better and it's much faster. It works better and it can basically solve the problem of the line dependency. Okay, now if there's no question so far, which is not, then we move to long short-term memory units, LSTM, and yeah, here I compared LSTM with GRU for better understanding. If you learn GRU properly, and then it's easier to understand LSTM. So note that for GRU, AT and CT were equal, but here for LSTM, AT is different, and therefore instead of CT minus 1, we need to use AT minus 1. And also, we don't have these relevant gates anymore. And instead of this relevant gate, what we have is called forget gate. It's a forget gate, and we show it with gamma F. And simply this forget gate provides the option to either keep or forget this previous value of CT to calculate the new value of CT. Another difference is the output gate, which also has its weights and biases. And you see AT is computed as the output gate times 10H of CT. So as you see, there are some similarities here, and it's better to move step by step to understand better LSTM and the differences between these. Again, yeah, we can show LSTM as well with like diagram. It might be a little bit more complicated, but if you follow the equation, you will see that it's the correct black diagram to represent these equations. And so these are basically the notations for multiplications. And we have forget gate, update gate, and then we have output gate. Yeah. Let me see. Yeah, there is a question in the chat. I guess we can answer later. Yeah. So RN basically cannot learn the long-term dependency, and we already talked about that and the reason behind it. But both GRU and LSTM were good to capture the long-term dependency. GRU is simple and fast in the answering the question as well. I think it's here as well, the question that was in the chat. It's much simpler and less parameter, and then LSTM is a little bit more complex and more parameter, that might be more effective in some applications. So now that we covered all the basic networks, we move on to integrated networks. So each of these networks has its advantages and disadvantages. For instance, autoencoders and recurrent neural networks are good at processing vectorized inputs and extracting the spectral features. And as we saw, CNNs are more powerful in extracting the spatial features. So it's a kind of logical to integrate these networks, aiming to exploit both advantages of different architectures. And in this case, for instance, see how convolutional RNN, it's an integrated network basically for convolutional RNN, that you have a kind of convolutional layers, and then RNN follows these layers. So now we move on to the experimental setup that we worked with, and most probably you found it in the paper and also in the codes that are available online. For autoencoder, we have 3 hidden layers with 32, 64, and 28 neurons. And we use ReLU activation functions. For RNN, we used 2 recurrent layers with GRU, each with 128 neurons. And for convolutional autoencoder, 3 convolutional layers with 32, 64, and 128 filters, and filter size of 3 by 3, or Kellner size of 3 by 3, and then 3 deconvolutional layers with 62, 32, and obviously P, the number of bands. Then we have convolutional RNN. You 2 recurrent layers with convolutional LSTM units, and 32, 64, and 128 filters, and size of 3 times 3 Kellners. So this is basically the experimental setup that we work with, and you will find much more details in the paper, and obviously inside the codes as well. And by the way, let me know if anybody could download the data and run the codes for any of the techniques. So now we are moving to their results. So we used 3 different data sets: Hyperspectral dataset, Indian Pine 2010, and Houston 2013, and Houston 2018, which both 2013 and 2018, Houston 2013 and Houston 2018 are available online if you want to. I believe that they were published for the Fusion contest in 2013 and 2018. So you can download it. And yeah, Indian Pines 2010, I don't think it's available online. So as you see here, we compare the deep learning techniques that we discussed. Autoencoder, recurrent neural network, convolutional neural network, convolutional autoencoder, convolutional RNN, and applying PCL prior to CNN. These are the deep networks that we use. So most of these networks are basic networks, and nowadays there are way more advanced techniques that you can find, and most probably they work better than these networks. And then we compare them with unsupervised feature extraction and random forest, and also supervised feature extraction techniques and applying random forest. So for unsupervised feature extraction technique, we used PCA, MSTV, which I didn't discuss, but most probably you can find all the details for this technique in the network. Is based on basically splitting and merging the bands of hyperspectral images to extract features. And then OTBCA that we discussed, orthogonal total variation component analysis, and LPP that is also we didn't discuss. It's kind of manifold learning or technique. And then for supervised feature extraction technique, we selected LDA that we discussed, and then CGDA and LSTR and JPlay that we discussed as well. And all the details about these techniques You can find it in the paper. So there are different types of techniques for supervised feature extraction as well. And then we compare all the results with applying random forest simply on the spectral bands, which, as you see here, it provides less information, less accuracies compared to other techniques for all the data sets, and which confirms the fact that feature extraction is useful, and either deep feature extraction or shallow feature extraction. So if you want to kind of summarize the results and the outcomes of the results here, you see, if you compare unsupervised feature extraction with supervised feature extraction, unsupervised feature extraction often outperforms the supervised feature extractions, or at least advanced unsupervised feature extractions. And then in the deep learning techniques or deep feature extraction techniques, as you see, so the integrated network that we recently discussed for all data sets, if you compare, like, for instance, convolutional autoencoder with autoencoder and convolutional RNN with RNN for this data set, you see that we can conclude that integrated network works better. And also, when you compare the results for all three data sets, you see that among deep learning techniques, CNN and PCNN works better, and PCNN works slightly better than CNN. So these two techniques, among all these techniques, works better, or deep learning techniques. But then when you compare deep learning techniques with shallow feature extraction techniques, you see them for Houston 2018, particularly for PCNN and also for CNN, you get considerable improvement in the classification accuracy compared to shallow feature extraction techniques. But for other data set used in 2013 and Indian Pine 2010, this is not the case. And so this is, as you see, for instance, here, LPP works slightly better than deep learning techniques, and here OTVCA works slightly better. But still, for instance, PCA is so close to, PCNN is so close to the other results, so it's not too far. So this is again the concept that I earlier was discussing, that there are some challenges, like type of architecture, like the CNN that we use here. You can design different type of CNN that works maybe better with different layers, with maybe more layers, deeper layers, and or another major challenge is the hyperparameter tuning. So if you, for instance, these results, we didn't change the parameter based on each data set. So it's a little bit hard to design your network, set the tuning parameter, and then you will apply your network on another data set. Even sometimes from the sensor in different, same sensor, but different conditions of capturing the data, you might not get good results. So these are some main challenges that we are facing with these kind of, because ultimately when we use deep learning techniques, we were interested in kind of an end-to-end algorithm. So less kind of parameter tuning and less or hyperparameter tuning. Yeah. So that was the three different results. You can find more details, like for instance, the class accuracies inside the paper if you're interested in for each classes, and how many classes each dataset has, and how many number of samples we use for these, and for the training and for the testing as well. So all these information are available inside the paper. So here you can see the comparison of the classification maps, and we also compare it with the ground reference that we had for, in this case, for Indian Pines 2010. We have the results of applying RF for hyperspectral bands, which is not as good as the others, and then LPPP, which was giving the highest accuracy for unsupervised feature extraction techniques. And then we have JPlay, which is the highest accuracy for supervised feature extraction techniques, and then CNN and PCNN, which was they give the highest accuracy between the deep learning techniques. And okay, the major, the first and major problem that you can face, or you can see here, you can observe that you have kind of over smoothing in your map for CNN and PCNN. As you see, for instance, this is probably a road that is highly over smooth, the borders of the roads, and also you can see all the other borders are highly over smooth, for instance, in this case and in this case. So basically there is less detail in these maps compared to the other maps. And that might be due to, you can solve it maybe with changing the filter size, or doing hyperparameter tuning, or any other any kind of tuning of the network. So that was the result for Indian Pine 2010. And here we compare the classification maps obtained for Houston 2013. Okay, part of this data sets are basically covered with clouds, as you see here. So these parts, it's not there is less information. We can't say there is no information, but there is less information because of the shadow, actually. So it's a kind of shadow covered area. This part and this, as you see, and it's not the problem of the network I wanted to mention. So again, we compared applying random forest on hyperspectral bands, and then you see the results of OTVCA, which for this dataset gives the highest accuracy, and JPlay, which highest accuracy between the unsupervised techniques, and I guess among all the other techniques as well. And JPlay also gives the highest accuracy between the supervised techniques and against CNN and PCNN, which provide the highest accuracies for between the deep learning techniques. And as you see, again, we are facing the same problem, over-smoothing problem in the maps, particularly in the case of PCNN. And we have less, this problem is much less in the case of JPlay, but then again, the accuracy is also very low. And also in the case of OTVCA, we cannot find slightly smoothing for this area, but not the other area. And it can preserve the structure of the or spatial structure, and that's or the edges of, and that's because of applying the total validation penalty. So yeah, and this is basically the grand truth of this data set that is available online. I believe that we share the training sample and test sample for these data sets, so you can reproduce the results of this data set for all the techniques that is inside the paper, and also I mentioned in the tables. Okay. We also compare the classification maps for Houston 2018, and this is actually the case that CNN and PCNN considerably outperforms the other techniques, and also the deep learning one and also the other ones. And OTVCA gives the highest among the unsupervised techniques, and JPlay provides the highest overall accuracy among the supervised techniques. And so as you see in this case, OTVCA actually kind of over-smooths this area, but PCNN and CNN can provide, can keep or preserve the specialist structure inside the scene. And so also at the same time they provide very high accuracy, which is kind of advantageous for this data set. So now, if there's no question, okay, then I conclude the talk or the tutorial. And then after that, let's see if anybody could install the or work with the codes or any of the codes, and if you need any how to work with the toolbox. Okay, so yeah, the limited number of training samples and selection of hyperparameters are main challenges for deep learning based hyperspectral image classifications. We mentioned this through the lecture. Also, we saw that unsupervised feature extraction techniques outperforms supervised feature extraction techniques in terms of classification accuracy, and by using the supervised classifiers. And the basic end-to-end deep feature extraction techniques, at least for two data sets, couldn't considerably outperform the shallow feature extraction techniques for hyperspectral classification. But then again, these are just very basic architectures, and we wanted to provide this toolbox for the researchers who are interested and the students they basically they can use these codes and they can come up with their own new ideas and provide, for instance, design a new architecture to improve these results. And we also show that hybrid models like SPC, CNN show superiority to both deep and shallow feature extraction techniques. So, yeah, I already mentioned this. The paper is called Feature Extraction for Hyperspectral Imagery, the evolution from shallow to deep. It's kind of an overview paper, and the toolbox is available to reproduce all the results. And I think you already have the link to the toolbox, and shortly I'll discuss the toolbox and answer your question if you have any problem to work with that. Okay, so I would like to appreciate Alexander von Humboldt's foundation, which basically supported my work in the past couple of years, and Helmholtz Institute Fiber for Resource Technology, particularly the machine learning group, so, that basically host me since 2020, and Helmholtz Zentrum Dresden Rossendorf. And special thanks to my colleagues and collaborators, Professor Jonathan Benediktsson, Professor Jocelyn Chanosat, Professor Shudan Kang, Professor Behnood Rasti, Professor Lalong Heng, and Dr. Danfeng Hong. And yeah, this is basically the end of the talk, and now I can move on to your questions. And then if you basically have any problem with the toolbox, I will be available to help. So I start with answering some questions here. I think we have 2 questions. One question is that I realize you compare RF and other deep learning algorithm. My question is RF a deep learning technique? And why not comparing your results accuracy with GB gradient boosting, which is an ML technique? No, obviously RF is not a deep learning technique. It's just random forest. It's a kind of conventional machine learning technique. But then again, the codes are available. You can compare it with any technique that you want. And as I already mentioned, the main idea behind this work was to provide a platform for the young researchers and those who are interested in this field to be able to get a kind of knowledge, kind of compact, in kind of compact form, and having a codes available after learning the methods to reproduce the results, and also kind of pave their path to easier design their own idea and their own the architecture in their mind. So actually, there are more, I already said there are much more advanced techniques that available online that you can also go and compare the results. The next question is, what do you think about using deep learning methods for semi-supervised classification of the hyperspectral images? Well, that's also kind of active area, and I think it's called kind of weak supervised classification, where you have a limited number of samples to classify, and I think there are so many papers on that topic as well, and yeah, there are some ways to deal with the limitation of the number of samples as well. There is another question. So basically, after I answer the question, I still don't see anyone has any question regarding the toolbox. Please go ahead and try it. I also try to explain a little bit myself if you don't have any question. So using deep learning methods, we can classify image with better accuracy. Can we use any deep learning method to remove shallow effect? Or can extract feature under shadow from very high spatial resolution data? Well, it's a kind of hard question to ask, to answer. Currently, I don't have any paper in my mind regarding, but I know that there are some techniques to remove shadows, deep learning techniques to remove shadows as well, and definitely deep learning ones as well. So if that is your question, I'm not sure if I got it correctly, but yeah.
Okay, thank you for the lecture and answering the questions, Dr. Rasti.
Is there any question on YouTube?
Currently, no.
Okay, so I can see that no, there is no question regarding the toolbox, and I would like to ask the audience if anyone tried the toolbox now.
Is it okay for our audience to reach you later via email for questions regarding the toolbox?
Yeah, sure. We already have so many questions regarding this toolbox. And yeah, if we have more time and no more question, I can kind of discuss the toolbox a little bit. And sure. So do we have more time?
Yeah.
Okay.
We have time.
So okay, I'll go and maybe share my screen again. Try again. So can you see my screen now? Can you see my screen?
The GitHub page.
Yeah. So yeah, this is basically a toolbox that I was discussing, and if you go through the toolbox, and you will see a folder for deep feature extraction, and then a folder for shallow feature extraction, which basically contains unsupervised and supervised techniques, and then you have the RF classifier as well. So these are all the techniques that we covered in this paper, and also you can find it in the toolbox as well. Principal component analysis, PCA, MSTV, multi-scale structural total variation, OTVCA, orthogonal total variation component analysis, LPP, locality preserving projections. These are all unsupervised feature extraction. And then we have supervised feature extraction technique, linear discriminant analysis, LDA, collaborative graph-based discriminant analysis, CGDA, LSDR, least square dimension reduction, and JPEG joint and progressive learning strategy. So these are basically supervised feature extraction techniques. And then deep feature extraction techniques that we discussed, stack autoencoder, autoencoder, recurrent neural network, convolutional neural network, CNN, convolutional autoencoder, and convolutional RNN, PCA, PCNN, which is PCA is applied prior to CNN. I'm not sure, I don't think we provided this, but you can easily apply PCA prior to your CNN. And then we have label sample for training samples and also test samples for use on 2013 dataset that you can basically use, and with the link that I send you for use in 2013 to reproduce the results. And this would be basically most of the information that you need. And I can see a question. Is possible to use your technique in an autonomous vehicle to remove the shadow effect? Well, these techniques are not designed for shadow effect, removing shadow effects. And we were not discussing these techniques for this application. So all the techniques that we discuss is well for pixel-wise classifications, and most of these techniques are not my personal technique, basically proposed by me. These are just very basic, for deep learning ones, they're just very basic architectures that we try to use. So, yeah, that was the last question. And still, if it seems that nobody is trying to work with the toolbox, but I'm available if anyone needs help.
Hyperspectral, we can't hear you.
Thank you. I guess we do not have any other questions remaining. Let me thank Dr. Rasti once again for the lecture. for information on the toolbox. Any participants are free to, of course, reach Dr. Rasti about questions relating to the toolbox data via email. Thank you again to the invited lecture. Thank you to the participants and attendees of this webinar session and the YouTube live stream. The summer school will continue tomorrow. Let me show the technical program. Tomorrow morning, we have the lecture Deep Learning for Fusion of Hyperspectral and LiDAR Remote Sensing Images for Classification, which will be given by Vencilayo from Witho and Ghent University, Belgium. And in the afternoon, we have the lecture Deep Learning from Remotely Sensed Data to Geospatial Semantic Information, which will be given by Claudio Persello from the University of Twente, Netherlands. Stop sharing. And if we do not have any other questions or remarks, I think that's it. Thank you, Dr. Rasti. Thank you.
Yeah, thanks for having me and inviting me.
You're welcome.
I hope that the audience got some kind of background in this field so they can basically come up with new ideas.
Okay. Then we'll be stopping the stream and the session. Thank you. Is there anything left to say, Professor Gülşen?
Thank you, Gora. Thank you.
Then I'm ending the session.
Thank you. Thank you very much.
Thank you, everyone. Have a good day.